Hi guys, I'm back. We're going to finish up 11.2. Sorry for me ending that lecture quickly. I had some distractions and I get distracted easy, lost my train of thought, and was making mistakes. So I figured I would just end that last lecture, ignore the last page. We're going to pick up about a page and a half where we left off on the last lecture. We were talking about geometric series. I said this is the form of a geometric series, a constant times the common ratio to the power n minus 1. It's not always n minus 1, but we're going to need to put it in this form in order to use our template. I said we would talk about it, and we will. We just haven't gotten there yet. So this was the last sheet that you saw, or the next to the last sheet that you saw in the last lecture, and I said that this geometric series converges if the common ratio is between 1 or -1, or equivalently the absolute value is less than 1, diverges otherwise. We showed a clever little algebraic proof to give us the sum of, or the sequence of partial sums, and we saw that the sequence of partial sums has a limit that's finite only if our common ratio is between -1 and 1. So we concluded this was our sum. So here's where I made the mistake right here. I forgot to put the power n minus 1, and I talked about several times how important that was. So it needs to be to the power n minus 1 in order for this template to hold. So I'm just backpedaling to that. We'll pick up there and we will do some examples. So that being said, we have our geometric series, a constant times the common ratio to the power n minus 1, and this converges if the common ratio is between 1 and -1. So keep in mind the absolute value of r less than 1 is equivalent to r being between 1 and -1, and diverges otherwise. Using clever algebra, I left up the -1, but this is important because this sum only equals the constant times 1 minus the common ratio if this is, so things that we have to look for, if that's n minus 1 and it starts at 1 to infinity, and we need these all have to match up. Otherwise, we have to rearrange it into this form so then we can actually find the sum. All right, so that being said, let's do a couple of examples. Oops. Let's look at n equals 1 to infinity, and we've talked about this guy. All right, now we want to get it into this form in order to use this template, because here we can see that our common ratio is 1/2, so r would be 1/2, but a here is not actually 1. We have to get it into this form in order to find its sum. So what we're going to do is we're going to rearrange this. I'm going to change this to 1/2 to the n power. So almost looks like this. Now we can see that our common ratio is 1/2, but we need an n minus 1 here. But notice, algebraically, this is equivalent. To drop this power by 1, I just pull one of the 1/2s out. So bear with me. This is going to be 1/2 times 1/2 to the n minus 1. So if we start here with n, and we need to reduce this by 1, up the power by 1, we just pull 1 out. If you think algebraically, we have the same base here. The power here is 1, the power here is n minus 1, so 1 plus n minus 1 would give us n. Now this is important because this is the one that now matches the template for the geometric series. So now we would say a is 1/2. R is also 1/2. So this converges since the absolute value of r is less than 1, and its sum is, well, it's a 1/2 all over 1 minus the common ratio of 1/2. So this is 1/2 over 1/2, which is 1. So therefore, 1 over 2 to the n equals 1 to infinity is equal to 1. Yay. All right, let's do another one. Okay, again, we want to get it into this form in order to use this template. So let's suppose we had this example, and I had given you this series, and I had 2 times 1/4 to the n minus 1 power, n equals 1 to infinity. This converges. It's a geometric series, right? Because r, the common ratio is 1/4. This power is not being applied to the 2. That's the coefficient out front. And the sum is a over 1 minus r, which is 2 over 3/4, which is 8/3. So if you add it, if you put 1 in here, just to give you, remind you what we're doing here, 2 1/4 to the n minus 1 power means, well, if we put 1 in here, we're at 2. Plus, if I put 2 in there, it's at 2 at 1 times 1/4, which is 1/2. If I put 3 in there, we get 1/4 squared, which is, so it's over 2 over 16, which would be 1/8. If I put 4 in there, cubed, 2 over 64. And if I added that up and I did this infinitely, it would all equal 8/3. Okay, again, remember it has to be in this form in order to use this template. So keeping in line with that, let's do find n equals 1 to infinity. Let's do something 2 over 6 to the n minus 1. Nope, actually I'm going to do 2 to the n over 6 to the n minus 1. Converges, diverges. All right, well, let's think about this. I want to change this to n minus 1. So this is equivalent to, remember, to reduce the power, we can make this 2 times 2 to the n minus 1, all over 6 to the n minus 1. Because 2 times 2 to the n minus 1 is just 2 to the n, which we have there. Now we can see I can bring that 2 out front of the fraction. And we can do 2/6 to the n minus 1 power. Reverse the quotient rule for exponents. And 2/6 is just 1/3, so I'm going to clean this up, and I'm going to call 2 to the nth power over 6 to the n minus 1 power 2 to the 1/3 times 1/3 to the n minus 1 power. So now it's in this perfect form. We're going from 1 to infinity. We have a power, needed power of n minus 1. My common ratio is 1/3. My coefficient out front is 2. So this converges because my common ratio is less than 1, and the sum is going to be 2 over 1 minus the common ratio, and 2 over 2/3 is just equal to 3. Kind of cool. All right, so I'll let you play around with some of those. You can ask questions. One more thing in this section. So this section is an introduction to series. Our concerns, or what we are looking for, is to determine if a sequence, a series diverges or converges. If it diverges, does it go to infinity, or does it just diverge, bounce back and forth between numbers? And then we also are interested in if it converges. Sometimes we can find the value. We saw with geometric series that converge, we can find the value of the series, but not all series we can actually find the value. We can estimate values, but not necessarily find them. In this section, they also introduce what we call a test for divergence. The test for divergence, TFD, as I'll say test for divergence, but I'll abbreviate it TFD, tells us if a series converges, then the limit of the corresponding sequence has to be 0. Right? In other words, if the limit of the corresponding sequence does not equal 0, equals infinity or any other number, then the corresponding series diverges. Now remember, this is called the test for divergence. It does not tell us definitely if a series converges. It just tells us if it diverges. So first thing you do is look at the corresponding sequence for a series. If the limit is not 0, then we know for sure that the corresponding series diverges. If the limit is 0, then the test is inconclusive. So careful. If the corresponding sequence converges to 0, the series may or may not converge. That is, if AN converges to 0, the test for divergence is inconclusive. So for example, let's look at n squared plus 3 over 2n squared minus 5 as n goes from 1 to infinity. What do we know about this? Well, let's take this as a series. Let's take the limit as n goes to infinity of n squared plus 3 over 2n squared minus 5. So we can treat sequences like their corresponding functions, and as n goes to infinity, we see we have a second degree over a second degree. This limit is 1/2. Now, because this limit is not 0, I can conclude by the test for divergence that this corresponding series diverges. Not 0, therefore by the test for divergence, n squared plus 3 all over 2n squared minus 5 is divergent. One over n squared, n equals 1 to infinity. What do we know about this? Limit as n goes to infinity of 1 over n squared is equal to 0. But this test is inconclusive. The test for divergence is inconclusive. All we know is that we can't conclude that it's divergent. So we know that 1 over n squared is convergent. Okay, we looked at that using an integral. But let's look at the harmonic series constructed from the harmonic sequence. Notice the limit as n goes to infinity of 1 over n also equals 0. Therefore, the test for divergence is inconclusive. Just because the limit of the corresponding series is 0 does not mean the series converges. As a matter of fact, this is a harmonic series. Note, we know that the harmonic series diverges. We looked at it, we compared it to the integral 1 over x. So this is inconclusive. So the only time the test for divergence is helpful is when the limit is not 0. When the limit is not 0, we can conclude that the original series is divergent. If the limit is 0, here's two cases. The limit of this corresponding sequence and this corresponding sequence are both 0, but this series converges and this one diverges. All right, so what we talked about, the harmonic series, we saw this is the harmonic series. We'll refer back to this. We're going to use this in future tests. Harmonic series, 1 over n, and we know that this is divergent. We saw geometric series. The geometric series converges to a over 1 minus r if the common ratio is between 1 and -1 and diverges otherwise. And then we talked about the test for divergence. It says if a series converges, then the limit of the corresponding sequence must equal 0. In other words, if the limit of the corresponding sequence does not equal 0, then the series diverges. If the limit equals 0, then the test for divergence is inconclusive. To do in Stewart, read 11.2, exercises 15 to 41 odd. I know this is a lot. You can do every other odd, but these are all good problems. 57 to 63 odd. Corresponding X, Y, Z homework. I forget what section that was. Let's see here. I don't know. You can look on. Can I put it here? Let's see. Yep. Nope. See Blackboard for the corresponding section. Sorry, I forgot to look it up. It's right in announcements. I'll write it in the 11.3 notes. All right, guys, keep working. Thanks for your patience. Hope everyone is well, and I'll talk to you soon. Bye-bye.